All right, hello everybody. We are going to prove section 11.2, number 11A and B. Actually, I was only going to do A, and then I looked at B, and it was really nice. So let's do A and B. All right, so 11A says, if G1 and G2 are loop-free, undirected graphs, prove that G1 and G2 are isomorphic if and only if G1 complement and G2 complement are isomorphic. So this is an if and only if. We've got two directions to prove. So we start off by saying, let G1 and G2 be loop-free, undirected graphs. And we're going to prove our first direction. And what we're going to say there is assume that G1 and G2 are isomorphic. And then I'm going to show that G1 complement and G2 complement are isomorphic. So that is, there exists a function mapping V of G1 to V of G2 such that the edge UV is an edge in G1 if and only if the edge F of U, F of V is an edge of G2. Okay, so that's what we've got. We have that there is a function mapping V of G1 to V of G2 such that this is the case. Oh, and it's 1-to-1 and onto. And such that. There you go. There's the definition of isomorphic. What I now need to show is that G1 bar and G2 bar are also isomorphic. And to do that, I'm actually going to prove that this same f, this same function, is also an isomorphism between G1 bar and G2 bar. And the way I'm going to do it, so I've already got that it's 1-to-1 and onto because the vertex sets don't change. The only thing I need to check now is this an isomorphism from G1 bar to G2 bar?
Hey everybody, let's take a break from the example for a sec. The example I'm doing here is really just a single example, and there are literally infinitely more problems you can run into on a discrete math exam. And odds are good you'll run into problems you've never seen before and be expected to apply what you know to solving them. But if you don't understand the content, you have no hope. So if you're taking a university, if you're a student taking a university discrete math course, and you're serious about not just getting a good grade, of course, yes, getting a good grade, but if you're serious about understanding the content, then go ahead and click the first link in the description down below and book a free call with me. Now, back to the example.
And so the only thing then to say is then notice that UV is an edge in G1 bar if and only if UV is not an edge in G1, which is true if and only if, because of the isomorphism, because of the if and only if I have right here, that's true if and only if F of U, F of V is not an edge in G2, which is exactly the same as saying F of U, F of V is an edge in G2 bar. And look what I've got there. UV is an edge in G1 bar if and only if F of U, F of V is an edge in G2 bar. Thus, what I've shown is that F, let's say it this way, F is an isomorphism between G1 bar and G2 bar as well. There you go. then G1 and G1 bar, G2 bar must be isomorphic as well. Now here's the thing, the other direction is exactly the same. So can I even get away without even doing the other way? Nah, it's a little bit harder to rewrite it the other way. So let's go ahead and do it the other direction as well.
Hey guys, if you are looking for help with learning discrete math or proofs, I know they're tough, then make sure to subscribe, as I'm literally going to be posting every example I have here for free on YouTube to help you learn and understand discrete math proofs. Back to the example.
So now I assume G1 bar and G2 bar are isomorphic. That is, there exists a G mapping V of G1 bar to V of G2 bar, 1-to-1 onto, and such that UV is an edge of G1 bar if and only if F of U, or I'm using G now, G of U, G of V is an edge of G2 bar. Okay, but notice that UV is an edge of G1 if and only if UV is not an edge of G1 bar if and only if G of U, G of V is not an edge of G2 bar if and only if G of U, G of V is an edge of G2. Thus, G is an isomorphism from G1 bar to G2 bar. And that does it. Both directions are exactly the same. So I feel like there's a nice, probably a better way to write this, but at least that gets it out. Now, sort of randomly, the second part of the question, part B of the question in the book says, determine whether the following graphs are isomorphic. And you look at that and you're like, right? They're big and complicated and really hard to see what's going on. How in the world am I going to show these are isomorphic? Well, take a hint from the question. It's part B of this question. You're probably going to use part A, and of course you are. If G1 and G2 are loop-free in the graphs, prove that G1 and G2 are isomorphic if and only if their complements are isomorphic. So there's the trick. Look at the complements. So I went ahead and did that already. Here are the complements of the two graphs. And the complements are really easy to come up with. Just just put the vertices in the same places and draw all the edges that aren't there. I drew them in red so they would stick out. And what you see, or what now is the question is, are the complements isomorphic? And I hope you agree, it's actually clear they're not, because the one on the left is actually a cycle. A, D, G, B, E, H, C, F, and back to A. It's just one big cycle. On the other hand, the one on the right is two squares. One square, two squares. The one on the right is disconnected. One on the left is connected. Clearly connected, clearly disconnected. And that, now I apply the theorem, G1 and G2, the G1 bar, G2 bar, G1 bar is certainly not isomorphic to G2 bar. Because clearly one of them is connected, one of them is not. Thus, by the theorem, we have the G1 is not isomorphic to G2. And that answers the question. Very nice little application. So hopefully that's useful to you. Have a good one.
Hey, thanks for watching. Remember, what I've explained here is just a tiny, tiny example in the literally infinite space of problems there could be that you'd run into. So if you're interested in really understanding this content, getting a good grade because you understand the content, go ahead and click the first link down below and book a free call with me, and let's talk about if I can actually help you do well in this course.